Hi, thank you for your interest in this topic. In the next few minutes, I'll be presenting our work that is on the impact of language familiarity in talker change detection. I'll refer to talker change detection by the acronym TCD. This is a joint work of Lauren Fink, Ahana Gangopadhyay, Sriram Ganpati, Venkat Krishnamohan, and myself, Neeraj Sarma. We all come from different universities, and it was a joy to work on this topic together and have our findings accepted in ICASSP 2020. The motivation for the work stems from three observations. Multi-talker speech is common around us, for instance, in meetings, audio podcast, and dinner table conversations. Yet the human brain easily detects who talked when, even on headphone listening, without spatial cues. In contrast, machine recognition of multi-talker speech is challenging. The word error rate is high compared to single-talker speech recognition. The literature states that talker change detection is crucial to understand or decode multi-talker speech signals. On the right, you see a time domain speech signal, and below it is the spectrogram. There are regions in the spectrogram where the pitch is steady, and there are also regions where the pitch has a dip or a sharp rise over a short interval of time. Tracking talker requires tracking the regularities and the deviations in the perceived features specific to a talker. Speech signal has multiple layers of information. The two dominant layers are the linguistic information layer and the indexical information layer. The linguistic information layer helps us to understand the phoneme, the word, and the sentence in the speech signal. And the indexical information helps us to identify the talker, the dialect, and the emotional state. It so happens that in natural speech perception, these two informations interact. The goal of this work is to explore the impact of linguistic proficiency on talker change detection for humans while listening to multi-talker speech stimuli. We also compare the performance with a machine system for the same task. As a solution to this problem statement, we propose to first design a stimulus set and then do a listening test on humans and quantify the results. Then we design a machine system and quantify the result for talker change detection on the same stimulus set. The stimulus set design follows the following approach. First, we have selected two speech data sets, one of them being the English Libri speech corpus and the other the Chinese IHEL speech corpus. Both of these speech corpuses have natural speech taken from audiobooks or from news broadcasts. On the right, you see a scatter plot where the y-axis denotes the average fundamental frequency of every file, and the x-axis denotes the speaking rate quantified in terms of characters spoken per second. You can see that there is a good spread in the fundamental frequency variation as well as the speaking rate variation for the audio files in these datasets. To create single talker stimuli, we concatenate two files of same talker with maximum feature distance in this space. To create two talker stimuli, we concatenate two files of two different talkers with minimum feature distance in this space. Further, we also select clean audio files by listening to the created stimuli. This is to reduce any channel noise or any ambient environment noise in the audio files. The stimulus set size is 50 single talker stimuli and 52 talker stimuli for each of the two languages. The listening test is quite simple. The subject listens on a headphone in a quiet listening environment. The trial is composed of listening to a speech stimulus, and at the end of the stimulus, the subject needs to give a response on the number of talkers present in the speech signal. After the response, there's a feedback and the trial ends. We store the response as well as the response time. To give a demo of two trials of this listening test, we will go to the next slide.
That will reduce the sum to 5,000 livres. She was married? Asked Aramis. Yes.
He is called, as you know, the Apostle of the Indies.
So he made him smell the vinegar mixed with incense.
Yeah, so this was a demo. You can see that in the second trial, the subject gave an incorrect response. In the participant population, we had 14 IISc students with a mean age of 24.2 years, and all were proficient in English but not in Chinese. So Chinese was the unfamiliar language in this test. To quantify the listening test results, we present the miss and the false alarm rate. First, focusing on the miss percentage. The blue color bars stand for the English stimuli, and the red color bar stands for the Chinese stimuli. You can see that the English stimuli have a miss rate of average miss rate close to 10%, which comes to around 5 stimuli. And the Chinese has a miss rate of close to 20%, which comes to around 11 stimuli. So that means humans are quite good at this task. They have a low miss. And further, it is interesting to note that there are lower miss for English, which is the familiar language, than the Chinese. And the results are significant. Coming to the false alarm, which is shown on the right, the English false alarm is close to 15, which comes to around 12 stimuli, and the Chinese false alarm is close to 10%, which comes to around 5 stimuli in a set of 50 stimuli. So again here it is interesting to note that the false alarm for English is higher than the false alarm for Chinese. So this hints that there's an interaction between the language proficiency and talker change detection performance of humans in this task. Next we come to the response time, and here we see that the response time is higher for English, that is a familiar language, than the Chinese. This holds for both correct responses as well as incorrect responses, and the results are again significant. We hypothesize that this happens because in the case of familiar language, as the listener is able to understand the speech, this imposes an additional cognitive load, and hence the response time is higher for English than for the Chinese. Coming to the machine system implementation, we use an already existing direction system for this task, and we adapt the output of the direction system to detect the number of talkers in this speech signal. The system works as follows. The input is a speech signal. This is segmented into 1-second chunks, followed by extracting the X vectors, each of dimension 512. For X vector extraction, we use a time delay network which is trained on voxelib speech corpus to identify a huge set of talkers. This pre-trained network is used here to extract the X vectors, which are then fed to a direction system. The direction system is implemented in CALD. It does 3 sets of operations: PCA followed by PLDA to do channel normalization and obtain and dimension reduction to obtain PLDA scores. These PLDA scores are then fed into a agglomerative hierarchical clustering framework where, based on a threshold criterion, the algorithm refines the number of talker clusters, number of distinct talker clusters. To get the output on number of talkers, we count the number of distinctly identified talker clusters. Here we see the machine system results. Interestingly, we can obtain a detection error trade-off curve for the machine systems by varying the threshold criterion in the agglomerative hierarchical clustering. Here we see the performance with the y-axis denoting the false alarm percentage and the x-axis denoting the miss percentage. You can see the performance is below par compared to the human subjects, and the Chinese as well as the English machine systems perform similarly. Although the direction system is a state-of-the-art direction system, however, it fails to work with good performance for the close to 7-second speech stimuli, which are the part of our data set. Generally, the direction system works much better if the speech signals are of duration in minutes. However, we see here that as the duration of the speech signal comes down to 7 seconds, this performance is a lot bad. However, the humans perform much better compared to the machine system. So in summary, we proposed the TCD experiment using natural speech stimuli. We found that the false alarm is higher and the miss is lower, and the response time is longer for familiar language when compared to the unfamiliar language. This suggests a link between perception of talker attributes and language proficiency for the task of talker change detection. Comparing the human response with a machine system, we see that the humans perform much better than the machine system, implying that there's a lot to be improved in the machine system when it comes to the task of talker change detection. Thank you for your kind attention. If you want to further look into the work, please feel free to go into the GitHub repo to see a demo of the work and also to see the stimuli used in this work. We'd like to acknowledge all the participants, the Pratiksha Trust Young Investigator Award, awarded to Sriram Ganpati, the Telluride Neuromorphic Workshop 2019, which brought all the authors together for this work. Feel free to contact us with any questions and suggestions. Thank you very much.